Hi class. In chapter 15, we are going to look at waiting line systems, what we call queuing systems. These are situations where you have something, we're going to call it something for now, and then we'll define it, something that is arriving at a point, and at that point, these somethings get served, get processed, get checked out, and they, the process is completed and they leave and go on to the next thing. So some examples of that are very simple examples, such as a supermarket, which is the one that you're going to have in your mind most of the time when I talk about queuing systems, right? You grab all your groceries, and you look for a cashier. You arrive at the cashier, you get in line, you wait in line. Eventually, the persons in front of you get served. You are then served, and you leave the system once you are served. That is the most simple example, but there are many more. We're going to talk about that. We can talk about how a plane gets boarded, how at a factory, how the components of a product arrive at a factory, and how those components are processed and eventually leave the system. They leave the process and they get transformed into something else. So there are a lot of applications for this. I think the book makes some really good references to either voting machines or polling machines, but I think they're voting machines. So like how people arrive to the polls to cast their vote. I think there are a few references to, if not, I'll make them references to sport events, how people arrive at the stadium and how they go into the stadium and how they leave the stadium. So we're going to look at that. We're going to look at the characteristics of these systems. What is it that we need to look at? How how they look, what they look like, what we need to look at, and how particular some of them are, how different some of them are. We're going to look at all of that. We're going to analyze them, and we're going to look at two main ones, and then we're going to relax some of the rules and expand it to other systems. So we're going to look at mainly at a single server waiting line model with Poisson arrivals and exponential service times. I know this means nothing to you at this point, but it hopefully will mean something to you in just a couple of slides. Then we're going to look at multiple server. Now you're probably like, oh, I picked up on that, right? One is single server, one is multiple server. Yeah, that's the difference between these two. So again, if you think of the supermarket, there's only one cash register, or there's more than one cash register, right? Then we're going to look at the economics of it, like how does this impact the bottom line? We're going to look at that, and then we're going to look at other more complicated systems. So I think we're going to look at a total of, I don't remember if it's 5 systems or 6 systems, but we'll look at all of them. So what is a, sorry, I look good. There. I just want to move some of my windows around, which I don't know if they're blocking you or not, but let me just move them out of the way. Okay. So what is queuing theory? Queuing theory is the study of waiting lines. What is not a optimization process, is not an optimization tool. We are now going to optimize these waiting lines, which is very different than what we have been doing up until now in this course, right? We have been doing a lot of optimization, finding the optimal solution, right? Maximizing this, minimizing that. We're not really going to do that in this case. What we're going to do is we're going to analyze the system, and we're going to look at the characteristics of the system to and figure out whether or not they're acceptable. It doesn't mean that we are going to design the perfect system. No, we're just going to figure out whether or not it's working, quotation, if it's within what is permissible. So here's the system. First time we look at at the system, the queuing system. So you have customers arriving over here, right? The customers are arriving. So if you think about the let's continue thinking about the supermarket, right? So you have the supermarket over here with the aisles with the food, and they're just going around and around picking up all their food, and eventually they got their cart full of stuff, full of food and others, and they're like, okay, I'm gonna go to the register. So they go to the register. You very well know exactly what happens. You try to spot the best one, right? We all do that. So they're just arriving, right? But they're not in the system yet, because they are in the supermarket. They're not in the system yet. Just like if you're going to a football, Gillette Stadium, you're not in the system just because you are in the parking lot. Okay, you arrive at the parking lot, but you're not in the system yet. You haven't arrived yet. But eventually, at some point, you queue up. You enter the system. That means you pick one line. In this case, this is a single server. There's only one line, but you enter the system. You are now officially waiting, right? You are in the queue. So you are in the waiting line here. You're going to wait, and eventually, someone is going to serve you. It's going to fill your order. It's going to take care of whatever it is that you need. Again, if you want to think about a factory, this could be materials like steel, and the steel goes into some kind of machine, and the machine processes steel, and after it's processed, it leaves the system. It's completed. We can say that this queue is over. You waited. You got processed, it's over as far as we are concerned. Of course, there could be another system that starts here, or this could be a final product, or it could be the beginning of another system. We don't know that. That's a different story. So the characteristics of any queuing system are going to be how people arrive into the system. It's going to matter. You'll see how much time people wait to get served. They wait to get to a station or to get to a person. Then is the priority that we are going to use to determine the service. Is it whoever arrives first, or is there some other order that we are going to use to determine who gets served first? So think about, for example, in the supermarket, it's whoever gets there first, right? There's always that person that comes in. Oh, can I, cut in front of you? I only have a loaf of bread. My opinion, no. Get back to the line. Get back to the back of the line. I'm in a hurry as well, right? Does that make me a mean person? But for example, when it comes to a plane, boarding a plane, there is not absolutely. If you're thinking, of course, it's whoever arrives first is the one that should get served first. Absolutely not in some systems. If you're boarding a plane, it's not whoever got to the airport first, right? Absolutely not. It's whichever system they have, and you know them. They're going to first call all types of special memberships and diamond this, gold that, and the other thing, and then when they go through all that craziness, then they're gonna go. They're gonna board the plane from the back to the front, or from the front to the back. If you're interested in all of that, there's a lot of research on that, and it's very, very interesting. I think we all think about that when we're boarding a plane. And then is the number and configuration of these servers. Is there only one register at the supermarket? Are there more than one register? And how effective are they? Are they different from each other? Are they the same? And if I am not, I believe in this chapter, this class, we are always going to assume that when you add a new server, that server is just as good as the one before, if I'm not mistaken. Okay, so the distribution of the arrivals. How people arrive does matter. And as we see different examples, it's going to make more sense. research has shown us that in most cases, Poisson distribution explains how people arrive at the checkout line at a supermarket or whatever other system we're talking about. It's random. Okay? Generally, people arrive in a random pattern. You cannot say, if you are the supermarket, that one person arrives every 5 seconds exactly. That is not true. That is absolutely not true. People arrive in a random pattern. Yes, there's an average, there's a standard deviation. We're going to use all of that. We're going to use all of those techniques. But in general, what we're saying is that people arrive in a Poisson distribution process, meaning randomly. We are going to relax that later on as well. But so it's something you need to pay attention in the problems. But it's our first assumption for our first set of models. And then there's the distribution of the service times, the time that it takes to actually serve you. So I'm talking about being here, right? So you're at the register. I'm sorry, you are waiting in line at the supermarket. Now you got your stuff on the conveyor belt. Now you're being served, right? That's what I'm talking about. So that time has been found to be exponentially distributed. What does it mean? In very simple terms, what it means is that it increases as the need, as that person's needs increase. So, for example, just to give you and this is a very simplistic explanation, but it works. I think it works at this level. If you only have one item, it's going to take very little time. The more items you have, the longer it's going to take to serve you, right? Isn't that true, right? If you call a help desk, the more questions you have, or the more complicated questions you have, but mainly the more questions you have, the longer it's going to take to serve you. So research finds that this is very well explained by an exponential distribution. Oh, sorry, just hit my mic. And this would be the formula for that exponential distribution. I didn't stop on the Poisson distribution because you already know the Poisson distribution, but I don't think you know the exponential distribution. I don't think we've seen it yet in this course. Okay, so keep that in mind. We're going to relax this later so we can have different models. As I mentioned before, the Q discipline matters, but we are going to only cover. It's a good thing that I have this note here, because I was going to say, do we ever relax this? And no, we are not going to relax that this specific topic in this chapter, in this course. We're not going to do that. So we're always going to assume whoever arrives first gets served first. Just keep that in mind. So I showed you before a single server system. So it's pretty simple, right? The customer arrives, they're gonna wait in line once they arrive, and then there's gonna be a system, a process, they're gonna go through it, and then they leave. That's a single server system. In a multiple server system, there's going to be a waiting line, and this is what the book is not very clear about this, but again, we're not going to cover all the systems, but we assume that if there's multiple servers, you just go right to the next one that is available. So like at a supermarket, you go for the one that looks the best. We're not going to spend much time on that. We're not going to spend any time at all in this course about that. It gets very complicated. But again, in a multi-server system, you just have multiple people or machines serving that queue, that waiting line. Okay. Yes, don't panic. Don't panic. I will post. I will send you an email or post something about this chapter. The way I am approaching this chapter is actually very similar to the way that I approached the chapter on inventory. I am going to go through it. I'm going to explain some of these. I'm going to explain some of the things about these models, not everything. I am not going to show you how we where these systems, where these models came from and how we derive them. The math is just it's just very complicated. There's no need for that. I just want to, all I want you to do is to know that they exist, understand them, understand the different structures, understand the lingo that we use in these systems. And I'm going to provide you with an Excel file and the tools so you can compute you can do the problems, compute these systems very quickly, very easily, and that's it. I don't want you to be writing the formulas because some of them are extremely complicated and so easy to just get incorrect on Excel. You'll see. But we're going to have a lot of variables, lots of variables. So first we're going to have lambda. So lambda is going to be the average arrival rate. So remember, arrival rate is how are people arriving into this system. All right, we call that lambda, is the average arrival rate. We're going to have 1 over the lambda, which is the average time between arrivals. We're going to use mu, is the average service rate for each server. So basically is how long does it take, what's the average time that it takes to process you through the register, or, the server. Okay, does it take 1 minute, 2 minutes? It's going to be the average. We're going to have the standard deviation of the service time, which we're only going to use a few times. And then we're going to have, now the following, let me just make sure. Yes, the following apply to all the systems we're going to see. You're going to have P0, PO, is the probability that the service facility is at idle, meaning there's no one in the system, there's no one waiting in the system, there's no one being processed in the system, nothing. There's nothing happening, which is possible, right? Sometimes you're in the supermarket, you're pushing your cart and you see a register, and you think you won the lottery, right? There's a register where there's somebody there at the cash register, and there's no one there, neither waiting nor being served. Beautiful, right? Because you go right in, you wait 0 time, and you get served. So that's what we mean, P0. Pn, so n could be 1, 2, 3, 4, 5, 6, right? Is the probability of n number of individuals, parts, whatever, in the system. So we want to know, like, what's the probability of 5 people being in the system? The probability of 10, of 1,000 people in the system, right? Either waiting in line or being served. But they're remember, in the system means you are waiting in the line or being served, okay? Not arriving nor leaving. PW is the probability an arriving unit must wait for service. So what are the chances that when you're at the supermarket, when you arrive, then you have to wait, as opposed to going directly into the system and being served? That's PW. LQ is the average number of units in the queue awaiting service. So on average, how many people are waiting in line, which is one of the crucial ones, right? Because this is the problem. This is the one that creates anger in your customers. Because once you're being served, even if it takes a long time, you don't care that much, right? When you go to the airport and you see the long line to check your bags, you get really upset. But once you get to once you get to talk to a human and you get to do your check-in and all that, you don't care if it takes 1 minute or 10 minutes. You don't care anymore because you made it past the line. So crucial, right? L is the average number of units in the system. And then notice how these 4 are kind of related, right? Like these 4 are related. These 3 are related and these 4 are related. WQ is the average time a unit spends in the queue waiting servers. So where LQ is the number of units waiting, WQ is the average time these units spend in the system, okay? So L is the number of units, W is the time they spend. And plain, just W is the average time a unit spends in the system. So if you want to remember this, it'll be helpful. L is about the number of units. W is about the time those units spend in the system. Okay? And when there is a Q, like here, LQ, is how long, well, in this case, how many are in the queue, in the waiting, being queued, okay, in the waiting. When there is nothing, is that they're in the system, just in the system in general. Here's another Q, right? So that's the time in the waiting, and this is the time in the system. So the time in the waiting versus the time in the system in general. All right. This is our first, here's our first model. And our first model has all of these formulas. What you're going to see, and sometimes I will point it out, sometimes I'll probably forget, what you're going to notice that of these 5-6 systems we're going to look at, some of the formulas don't change, some of them change, and some of them are the same in some of those models. So we're going to have a lot of, we're going to be using like this, kind of like the same formulas, but in some cases they're going to be modified, in other cases they're not going to be modified. But we're always going to have a formula for each of these pieces, which we pretty much need every single time. We need a PO, an LQ, an L, a WQ, a W, a PW, and a PN. And these are the formulas. No, you don't have to memorize them. No, again, you're going to have an Excel file that is going to compute this for you automatically. I just want you to be aware of them in case you ever need to do this manually, or you lose my file or whatever you want to, whatever happens. You can go back to the book and you know where to get those numbers from, right? These formulas. So I'm not going to read them. There's no point. But I just want you to be aware. Something else we need to remember is the concept of steady state operation. Okay, what we assume that when a restaurant opens, when a business opens, there are no units in the system. There are no customers in the system yet. That's one assumption that we need to make. You cannot make the assumption that for the models to work, that is, that as soon as you open, all the units, all the customers come into the system immediately, like in a big bulk. I'm not saying that doesn't exist. Of course it exists. I know every time they have like a new sneaker or they sell concert tickets, right? There's like the people waiting. Oh, of course, like some big holiday these promotions, whatever. People are waiting for days, right? When the doors open. I have to confess, I'm sorry, I am not even aware of a model for that. I don't even know if it exists. I'm not an expert on this. I've only seen this in manufacturing, so I'm not sure if there's a mathematical model to model craziness. So once the system opens, in this case, like as a restaurant, for example, there's a gradual activity that builds up until it reaches some normal stage, what we call the steady stage. So you think, for example, of a cafeteria or a restaurant. It opens the doors, there's no one. Then one individual arrives, 2, 3, 4, and then eventually it reaches this steady state of operation. That's what we care about. We don't care. We can't apply our model for let's say that the supermarket opens from 6 a.m. to midnight. There's really no point in applying this model at 6 a.m. in the morning because you know that it's going to be empty. The supermarket has not reached that steady state. It just doesn't make any sense. Now, there are businesses where you need to be aware of these steady states, and there could be multiple steady states, and you may have models for different hours of the day. So, for example, if you are talking about a fast food restaurant, you could have multiple steady states throughout the day that you are aware of. So there's like the noon time, and then the evening, dinner time, that's perfectly fine. The period between the beginning of the process and the what we call the startup until you reach the steady state is called the transient period. Okay, during this period, the transient period, customers are just arriving and being served, but we can measure that. Once it ends, you enter the steady state operation. And again, that's what we are going to be talking about. That's what waiting line models describe is the steady state period. We are going to use very specific lingo as usual, and we actually have this is one of those things that I want you to know in case you are ever faced at work with one of these things, so you know what people are talking about. You may not remember perfectly, but that's perfectly fine. That's okay. But at least you will know, like, oh yeah, I'm aware of this. I just need to look it up to see what it means, but I know how it's structured. So in queuing systems, we use a 3-part code, A, B, and then K. No, A is never A nor B. It's just a placeholder. But it's a 3-part system. Okay. So, for example, the first character, in this case A, identifies the arrivals. B, the second component, identifies the partial distribution, meaning how is that being served. And K is the number of servers. Is it 1 server, 2 servers, 3 servers? Okay. So, for example, if the arrivals and the service, when you're being served, if they follow what we call a Markov distribution, this is new. You've never heard the word Markov in this class up until now. I don't think we're going to get to that chapter. But if you hear this, the Markov system assumes both a Poisson arrival and an exponential serving, which is exactly what I told you before. This is like the base model that we're going to use. So we use the letter M. So you will see M will be the first code for the arrivals, M again for the serving time, and then K will be the number of servers, which I will explain in a second. If you see a D, it means it's deterministic, constant. If it's a G, it will be general distribution. So again, if it's a Poisson exponential, you will have an M. If you have arrivals are Poisson, but the serve is general distribution, it will be MG, and then the number of servers. So K is the number of servers. So if you have 1 server, that will be a 1, 2, that's a 2, 3, 4, 5. As many as you have, it will replace that K. So the one that we're going to start with is an MMK. So that means that arrivals occur in a Poisson distribution. The service is of exponential distribution, and there are K number of servers working at identical service rates as I mentioned before. And so the first example is going to be a single serve. So it will be MM1. Okay. And again, when we have a MM system, a double M, which means Poisson and exponential, we call that the Markov. That's why it's an M. Yes, I know. I think D is for deterministic. That makes sense. G is for general distribution. That makes sense. How come when we use Poisson and the exponential, we get an M? Yeah, I don't like it either, but you can thank Markov for that. Okay. Okay, I'm gonna pause here, and the second, and we'll go on to the second part, the second video, and we are going to cover our first model, which is going to be an MM1, meaning Poisson arrivals, exponential server with a single server, MM1. As you can see, single server, Poisson, etc. Okay, thank you.